In this video, we're going to look at two problems in which we calculate reaction forces. This problem appears as an example in pages 7 and 8 of the course notes, and we're looking at a bridge which has two supporters in place and three forces acting upon it. In order to solve this problem, we're going to make use of the three equations of equilibrium that we encounter in the course. So firstly, we know that sigma h, or the sum of all the horizontal forces, is equal to 0. So there's no overall horizontal force, they balance out. Secondly, we know sigma v, the sum of all the vertical forces, is also 0. All vertical forces must be balanced. And lastly, we know the moment, sigma m, taken at any point in the structure, must also be 0. There's no rotational motion. This is a static structure at equilibrium. And we are asked in this problem to find three things. We're asked to find two forces that apply at point A, so HA, a horizontal reaction, VA, a vertical reaction, and we're asked to find VB, this is a reaction at the support letter B. And it's important to remember the reactions can only take place at support, so we know that this is a total sum of all reactions because these are the only two supports. We know that there'll be no moment reaction at point A because it's a hinge, and we know there'll be no horizontal reaction at point B because it is a roller. Let's remove those circles. So we start off in this problem by looking at what we can identify straight away. And we can see in the problem that we have a single horizontal force being applied, 50 kilonewtons acting to the right. And because B is a roller, we only have a single horizontal reaction force of HA acting towards the left. Now, we could immediately, and it would be acceptable to point this out, say that HA must be equal to 50 kilonewtons acting towards the left to balance out the force. And it does, that's the case. But for completeness, and because this approach will be applied in more complicated examples, let's state this. So what we say is that sigma h is equal to 50 acting to the right minus HA acting to the left. And this, of course, from our equations of equilibrium, is equal to 0. Rearranging that simple matter of saying HA is equal to 50 kilonewtons. And if we want to be specific, we could indicate that this is acting towards the left-hand side. It's a negative force acting to the left of the diagram. And so we've dealt with the horizontal force. Now we have the matter of the vertical forces to deal with. What we can see in our diagram is that we've got two vertical forces acting downwards at 160 kilonewtons and 80 kilonewtons. And we have two vertical reactions. We have VB here and VA over there. So the total downward force is equal to 240 kilonewtons, which means VA and VB in some combination must be equal to 240 to counterbalance that. But we don't have enough information from solely looking at the forces, so we can't use our sigma V equals 0 equation just at this point. What we need to do is to invoke the equation for moment. Now, we know if we were to take the moment at any point along this beam, the moment supplied by VA is going to be 0. And the reason for that is it's a hinge joint. So if we were interested in finding out the moment, there would be no moment coming from this support here. It's not going to act against rotation because hinges are designed to allow rotation to take place. So we want to then find an equation that has VB in it. So if we instead work out what the moment is around point A, then we'll find that VB must make a contribution to this because it's acting upwards at a distance from VA. And so this will allow us to find an equation in which we can find the value of VB. So let's do that. So we are interested in point A. So we're going to say we're finding sigma m, and we write a little subscript A here to say this is where we're doing the moment, because unlike the horizontal and vertical forces which sum across the whole beam, although the moment's always 0, it's measured relative to a particular point. And the moment at any point is given by forces that are acting on the structure and the distance at which they're acting from the point we're concerned with. So let's first of all take all of our applied forces. If we consider this force first of all, the 160 kilonewton force, the arrow I'm drawing here, you can see that this is acting the length of 2 squares away from VA, from A. And each square is 2 meters long, so that's a total of 4 meters distance. That means the moment is calculated by the force it's acting, which is 160, multiplied by the distance it's acting at, that's multiplied by 4 there. So we can see the moment contributed by this particular 160 kilonewton force is 160 times 4. We'll then consider the vertical force, vertical moment due to the 80 kilonewton vertical force. So again, if we look at the distance, I've drawn this green line here. This is the distance from point A. You can see that the 80 kilonewton force is being applied at a distance of 6 boxes, each one again being 2 meters wide. So that's a total of 12 meters. So we can then add, because it's acting in the same downward direction for a clockwise turn, 80 times 12, because it's 80 kilonewtons 12 meters away. But we also have to consider the horizontal force here, because a horizontal force applied to the right is going to also have a turning effect, because it's applied at a distance from the force that's been applied at this point here. This is where we're experiencing the force relative to point A. And this point, because again it's a square, is 2 meters from the point in VA. So this is also contributing to a turning force, and this is a force of 50 times 2 meters. So there are all the moments due to the forces acting to turn this beam in a clockwise direction with respect to point A. Now, we know there's only one reaction force reacting against this at this point, and that's VB. So VB has to act against this to make sure the total moment is 0. VB, if we look again at our diagram, I'll draw another line here, it's a wee bit crowded, but I'll draw this on, is acting a distance of 4 boxes away from A, and so that's 4 times 2, that's 8 meters away. So what we can say is we must be able to subtract VB times 8 to make sure that this whole thing is equal to 0. Because we know the structure is not rotating, so we know our total moment must be 0. So if we do this, if we add these up, all these values, we're going to get 160 times 4, which is 640. We'll just do all of this in black pen. We've got 80 times 12, which is 960. And we've got 50 times 2, which is 100. And that leaves us with minus 8 times VB. We want to rearrange this just now because we want to find VB. So taking VB over to the other side and then dividing everything through by 8, we're left with VB is equal to all these numbers added up together, which is 1700 divided by 8, and that there. And that leaves us with, I'll just do my calculation to check that I'm getting this right here. $212.5. Of course, that is in kilonewtons and it's acting up the way. Now, where does this leave us with regards to finding VA? Well, I'll just make a little space here just to show it's separate from the rest of it, and we'll do it down here. Well, remember what we said at the beginning. We know the total vertical force is going to be equal to 0. And we've got two forces that are acting up the way. We've got VA and we've got VB acting up the way. We've got two forces acting down the way, our 160 and our 80 here. So we know that VA plus VB minus 240 has to be 0. But we've now worked out what VB is. So we've actually got VA plus 212.5 minus 240. Make that look a bit more like a, whereas Rob, that made it look like a plus there. I'll just do it again because it's a wee bit messy. And then I've got VA plus 215.5 minus 240. And so we can rearrange this as well to get a value for VA. And putting that into our calculator as well, because I'm taking no chances here, gives us 27.5 kilonewtons, 27.5 kilonewtons, and also that force is acting up the way to counterbalance the downward force. So what were we asked to find? We were asked to find HA, and we have done so here. We're asked to find VB, one of the two forces acting up the way, and we've done so here. And we're asked to find VA, which is the other vertical reaction, and we've done so here. So that has been everything we sought to find. And what we have done is we're able to use the horizontal equation of equilibrium to find HA, but we couldn't use the vertical equation of equilibrium to find VA and VB until we'd looked at the moment. And that's exactly what we've done in the second part here. Found VB, and that's allowed us to use that in combination with the vertical forces equation to find VA as well. So that's everything we'd hoped to achieve in this problem, and we've done it. The second thing we looked at is an example in class, and I'll just move my whiteboard along here with this problem here from the tutorial that I showed you at the end of class. Now, what I'm going to do here is I'll redraw this diagram because we're going to deal with these little circles here. These circles represent a uniformly distributed load, and what that means is that if it says 1.5 kilonewtons per meter, that means for every meter of beam or whatever the structure is here, there's 1.5 kilonewtons applied as a force. And in this particular case, we have a 3 meter long beam. So if there's 1.5 kilonewtons per meter, 1.5 times 3, I'll just write that down. 1.5 times 3 is equal to 4.5 kilonewtons. So the total force due to the UDL, uniformly distributed load, is 4.5 kilonewtons. And when we're presented with this in a problem, in terms of how do we deal with this in terms of our equations, what we do is we add this force at the center of the UDL. So it would be somewhere like this on our diagram. We'd be effectively adding a force of 4.5 kilonewtons, and that would be halfway between the two ends of the beam. So in this particular case, this is 1.5 meters from this end, and also 1.5 meters from that end. Now, this makes the diagram look a bit messy, so I'm going to quickly draw another beam just below another structure here and put on those two forces and our two reactions. So if we imagine a beam like this, in fact, I can be a bit cleverer than that. I can use the ruler here and get a nice straight line for it, which is what I'm going to do. My roller's not enjoying this. Okay, perhaps that was more trouble than it's worth. Unless I find a shortcut, I won't be using that again. But it does actually help when you're drawing freehand to have something like this. So if I come back to my page, I can draw, which will hopefully now be a straight line. I'll leave you to be the judge of whether that was worth the effort in doing so. So as before, we know we have our two reaction forces here, and these would be in the form of probably supports in our real world problems that R1 and R2, or R2 and R1 have drawn them. We know that at the 1 meter distance, we had this 6 kilonewton force, and at the halfway point, we have this 4.5 kilonewton force here as well. So this is 1 meter away, and this is 1.5 meters away, and the implication is the rest of that's 2 for the 6 kilonewton force and 1.5 on the other side of the 4.5 kilonewton force. So we know what our beam looks like here. And so we think back to our equations of equilibrium, but we don't have any horizontal force acting here, so we've got no interest in using that equation. We do have vertical forces acting, but as in the previous problem, we have no way of identifying how big R1 and R2 are without looking at the moment first. Now, for a problem like this, there's no reason in particular to pick either end of the beam. The moment's going to be 0 at either end, and again at both ends of the beam we'll be given an equation that involves the other force. So if we take our moment at the left-hand side, we'll gain an equation that gives us R2. If we take our moment at the right-hand side, we'll gain an equation that gives us R1. So just for no particular sake at all, we'll take the left-hand side, we'll take the moment there. So I'm going to call this sigma, a messy sigma sign, sigma M1. And that's going to be equal to the moment due to all the forces acting relative to this left-hand side of the beam here, this point here. So we're going to take the moment of each force relative to this point. So a systematic way to do this is either to consider all the down forces and all the up forces, or consider that the forces acting from left to right, and both of them actually are the same approach in this case. So what we've got here, and let's take the positive forces first, positive moments I should say, we're going to have R2 scratch that, it's acting counterclockwise, so the downward ones will be the positive ones. It doesn't really matter as long as you keep the same convention all the way through, but it's better that you're always using the same convention through all problems. So the downward forces here are causing the clockwise rotation, so let's stick with that. So we've got the 4.5 kilonewton force acting at a distance of 1.5 meters. We've got the 6 kilonewton force acting at a distance of 2 meters, and we've got subtracted from that, because it's acting in opposition to it, we've got as yet unknown reaction force R2 acting at a distance of 3 meters. And we know that the sum of these must be 0 because we've got no movement. So if we work this out, we're going to if we work this out, we're going to have 4.5 times 1.5, which is going to be 6.75, plus 6 times 2, which is 12, minus 3 times R2 equals 0. So as in the previous problem, we did a bit of rearrangement to give us R2 is equal to 18.75 divided by 3, which is 6.25 kilonewtons acting up the way. And now it's a simple matter of using our vertical force equation to work out the vertical forces here as well, because we now have 3 of the 4 forces acting. We've got 2 acting down, we've got 1 of our 2 forces acting up in the form of R2. So we can work out the equilibrium equation for V. So if we do that, let's start off with our forces acting up. We've got R1 plus R2, and we're taking away from them our forces acting down, which is the 4.5 kilonewton force and the 6 kilonewton force. We can put into this equation our value for R2, which we've just worked out. So we've got R1 plus 6.25 minus 10.5. And we know this is equal to 0 because, again, there's no movement in this structure, so the sum of all the vertical forces must be 0. And that leaves us with R1 is equal to 4.25 kilonewtons acting up the way. And that's how we use our equations of equilibrium in these examples to work out the reaction forces to the applied forces on the beam. So hopefully that's been helpful. There's another 5 problems like this in the tutorial, and so we'll be having a look at those in the next class.